Good day. My name is Theorems1-6.
And my name is Robert Seth Magallanes.
Today, we'll present to you the Theorem 1 to 6.
We hope you learned something from our video. Enjoy!
Theorem number 1. Two intersecting planes meet in a straight line. To represent this theorem, I have shown you this figure. So therefore, I conclude that these two planes intersect in a straight line, which is A and B.
Okay. Theorem 2 states that a plane is determined by a line and a point not on the line. Second, by two parallel lines. And third, by two intersecting lines. I will use this figure to demonstrate to you Theorem 2. To prove that in each case a plane is determined. In the first case, let A and E be 2 points on line L. One and only one plane can be passed through line L and point S, because according to axiom 2, one and only one plane can pass through three non-collinear points, which in this case are points A, S, and E. On the third case, by definition, line 1 and line 2 lie in this plane. Let Q be on this line and S and R be on this other line. Using axiom 2, we can now say that a plane can be determined using these three non-collinear points.
Theorem number 3. If a line is perpendicular to each of two lines at their point of intersection, the line is perpendicular to the plane of these lines. To prove this theorem, we must prove first that this line 1 and line 2 lies in the plane M by theorem number 2, which states that two intersecting lines determine a plane. Then by definition, this one line perpendicular to line 1 and line 2. If line 1 and line 2 are on the plane M, then plane M is perpendicular to this line.
Theorem 4. Theorem 4 states that through a point, there is one and only one plane perpendicular to a line. I will use this figure to demonstrate to you Theorem 4. To prove that whether this plane is perpendicular to this line, we must first prove that these two lines are in this plane. Now to prove that, again we must use Theorem 2, which states that two intersecting lines determine a plane. Now we have a plane. So by definition, we have this line that is perpendicular to this line. So if these two lines are in this plane, then this plane is perpendicular to this line.
Theorem 5. Through a point, there is only one and only one line perpendicular to the plane. To demonstrate this theorem, I will use this figure. When P is in the plane M, let line 1 be in any line in a plane M through P, and let N be a plane perpendicular to line 1 at P and meeting M in line 2. Let PA be a line in N and perpendicular to line 2. Then PA is also perpendicular to line 1. Therefore, P and A is perpendicular to M.
Theorem 6. Theorem 6 states that oblique lines from a point to a plane meeting the plane at equal distances from the foot of the perpendicular are equal. And conversely, two equal oblique lines from a point to a plane meet the plane at equal distances from the foot of the perpendicular. Given PC is perpendicular to plane M and AC is congruent to BC. To prove that oblique lines PA and PB are congruent, we must first prove that triangles PCA and PCB congruent. We can do this by using the SAS postulate or side angle side postulate, because two of their legs are already equal and the angle between these legs are perpendicular. And by the way, perpendicular angles are always congruent. Having proven that these two triangles are equal, therefore we can now prove or conclude that PA and PB are congruent because corresponding parts of congruent triangles are congruent.